Hello guys, so welcome to our lecture 13. In this lecture, we're going to continue our discussion about combinational circuit. And here is another example, which is basically the binary adder-subtractor circuit. So we studied the adder. We studied also some modification of it so we can get subtractor out of this adder. So basically the same foundation, the same circuit, with minor modification can be used as a subtractor. We didn't do any, major changes for the subtractor. So now the question is, can we design a circuit that can do both at the same time? I mean, can do addition if the user wanted to do addition, he can do addition. Then if he wanted to do subtraction, he can do with the same circuit subtraction. And the answer is yes. But for that, we need a kind of selection mode, we can say. So if the user wanted to make some addition, he can set this mode to add mode, so he can add the two numbers of the inputs. If you want to subtract, he can, play with this mode, okay, make it subtraction mode, then we can do the subtraction, okay. So basically, we need something that has two states, different states, of course. So when it's in the subtraction mode, it has some distinct value. And when it's in the addition mode, it has another distinct value, okay? So we need just one bit because one bit is either 1 or 0. So we can, for example, set the 1 for the addition or subtraction, whatever, and set the other value. If you choose 1 for the subtraction, then choose 0 for the addition or vice versa. Okay. So it will be really, very simple circuit. We just need this bit here. Then with another minor modification, we can achieve our binary adder-subtractor circuit. And here is a circuit in front of us. Okay. A and B are 4-bit numbers, binary numbers, of course, okay, that we can either subtract or add, whatever we want, okay. So, and here is the mode bit. So this is the mode bit. When the mode is 0, when the mode is 0, we're gonna add. And when the mode is 1, we're gonna subtract. Good. So remember in the addition, we wanted the input carry to be 0. Okay, this was just our our requirement for the addition. So look guys, for these x and y, so x and y are just representing A and B in different states, okay, or different modes basically, okay. So for the addition, we wanted to add A and B. So the input carry, this carry C0 is 0, as you see, guys. Okay. And we need just to assign A to X, or X to A, or A to X, and B to Y directly. So in the addition, we can say that xi equal to ai here for the bit 0, bit 1, bit 2, bit 3, because we have 4 bits. And yi is basically bi. How about subtraction? If you remember, guys, for subtraction, we did a little bit, a small, I'm sorry, this is also plus. We did a small modification. So we convert the subtraction into addition by taking the 2's complement of B. And 2's complement is basically the first complement B bar plus 1. So we're gonna make the carry input 1, and instead of inserting B directly, no, we're gonna insert B into an inverter, and we take this output of the inverter and put into the full adders, the 4 full adders. Okay, this way we can just use the same circuit, the addition circuit, I mean. Okay, so let's look at X and Y in that case, the subtraction case. So when the mode is 1, I mean, we want to make a subtraction. Still, subtraction here. Let's do it with another color. For the subtraction, now it's still Xi is equal to AI. The trick was made for B. But now Yi is equal to Bi complement. That's basically what we have here in the table. Okay? And the carry is 1. So this carry will be 1. Now look at this table and try to deduce or derive expressions or a design for the interface that we kind of made for B basically before entering it to the circuit, to the full adders basically. Okay, look at Xi and the AI. So basically in both cases, when M is 0 and M is 1, X is just equal to A. I mean Xi all the time is equal to AI. So basically X equal to A all the time. And that's why here A0 is connected to X0, A1 is connected to X1, A2 is connected to X2, A3 is connected to X3 directly. But the difference will appear for the Y's. When M is 0, Y is equal to Bi. When M is 1, Y is equal to Bi complement. Okay? So you can do that in this way. You can define a function for Y related to B in that way. You can say that Y is equal to, you can say when M is 0 means M bar or M dash or M prime times Bi or times, so let's say the AI Bi, here is Yi Bi. Then when M is 1, so plus 1 plus M, then multiplied by Bi complement. And you can then verify. If you put M equal to 0, with M equal to 0, so this term will go away. So at that time, Yi will be equal to Bi. Because M is now 0, so Mi complement will be, or M complement will be 0 complement, which is 1. And when M is 1, so M complement will be 0, so the first term will go away, and we will have only the second term. Second term is 1 times B bar, so it will Bi bar, so it will give you Bi bar. So Y at that time will be Bi bar. Okay, and let's look at this function here. This is basically XOR. So Yi is basically M XOR Bi. So these are the two functions. And that's why we have here 4 XORs. So for example, Y3 is B3 XOR M. Y2, B2 XOR M, and so on. Finally, what is CO? So if we look here, look guys, when M is 0, CO is 0. And when M is 1, CO is 1. So basically here, we can say that CO is all the time equal to M. And that's why here we have M is connected to CO all the time. Okay. Now let's do a check. Let's see if we can really add or subtract based on M. So let's add M with 1. So let's remove all that explanation here. and put m equal to 1 times, then equal to 0, and see what we are adding exactly. If we add a and b, this is basically adding. If we add a and b bar and 1, then we basically make subtraction. So let's with blue, put m equal to 1, which is basically subtraction. So c will be equal to 1. This is the first line of subtraction, because in subtraction we need a 1 here at the c input. A naught is x naught, but then how about b naught? So this is 1 and this is b naught. So 1 XOR b naught. This is basically 1 b naught bar plus 0 b naught. This is will go away, so we'll end up with b naught bar. So this will be b naught bar. So the first half other will add a0, because x0 is equal to a0. A0 plus b naught bar or b0 bar, and there is a carry of 1. That's basically, you know, the subtraction, exactly the subtraction. And of course this will be repeated. So this is b1, and here is 1 at the input, so this will be b1 bar, and so on for the rest. b2 bar, b3 bar. Now let's do the addition. So let's try the red now and put m equal to 0. So the carry will be, the input carry is 0. That's what we want. Good. Still x naught is a naught. x1 is a1, x2 is a2, x3 is a3, just like the subtraction, no problem at all. But this now becomes 0. So let's now check 0 XOR b naught. This is 0 b naught bar plus 1 b naught. So this is basically b naught, not b naught bar. And this is b1, this is b2, this is b3. So if for other one, inputs are a0, b0. For other two, and carry 0. For the other two, a1, b1, carry of the first, you know, stage, and so on. So that's basically addition. So with one circuit, we can do both addition and subtraction. Okay? But one may say here, it's not a formal way to design a circuit. I mean, in all the circuits that we discussed so far, guys, for example, the BCD to XS3 design example, the first example that we take in combinational circuits, okay, we build the truth table, and from the truth table we make some we build a Karnaugh map. Then from the Karnaugh map we minimize the functions, the outputs, and you know we build the circuit, and the same for full adder and same for the half adder. Okay, but where is the truth table here? Okay, this is, you know, a little bit of hierarchical modeling or design, plus some behavioral design as well. These XORs are behavioral design. Okay, and still we can do it in a formal way. I mean, with a different kind of truth table, it's still truth table, but with not zeros and ones. So let's do that formally now. This is of course correct, and you know everything is fine, but we can do that formally. So and this is basically our truth table here. This is what we see here, a truth table. Okay, and we can deduce formally the functions. I mean, y is equal to whatever, which is m XOR b, and the a c is equal to m, c naught is equal to m, and the a is equal to x is equal to a, formally from that truth table. So let's see how this. To explain how, I'm gonna go away a little bit to explain to you how to deal with such truth tables that doesn't have only zeros and ones. So all the truth tables that we discussed so far have only zeros and ones. This truth table has variables a and b. Okay, so let's assume we have a circuit like this, digital circuit, of course. and it has an output function here. It has 4 inputs: X, Y, A, and B. It's 4 inputs. But we can express this in a way that based on the value of X and Y, F will be some function in A and B, whatever A and B is. So let's assume that the function is like this: X and Y, and here is F. 0, 0, 0, 0, 1, 1, 0, 1, 0, A, 1, 1, B. What does that mean? When X and Y both zeros, F will be 0 forever. When X is 0 and Y is 1, F will be 1. Okay? But when X is 1 and Y is 0, F will equal to A. Whatever A is, if A is 0, then F will be 0. If A is 1, F will be 1. And finally, when X is 1 and Y is 1, F will be equal to B. Whatever B is, B can be 0, at that time F will be 0. B can be 1, at that time F will be equal to 1. But look at this truth table. This is a different truth table. Because some values here are not known. It's just based on some variable, which is A and B. So how can we get a function? How can we use the Karnaugh map to do that? So it's still easy. So we're gonna have a Karnaugh map like this. We have here 2 variables, so we have the simplest Karnaugh map. Not the simplest, by the way. There is, as we will see after a moment, there is, simpler than this. Here is X, here is Y, 0, 1, A, B. Okay? In the Karnaugh map, when we combine a group, we combine a group that has similar stuff. Either the group should have all ones or all zeros. Okay? In some examples, we do examples in which we group the zeros, not the ones. For example, for F bar, F complement. So here we have 3 groups: this guy, and this guy. So F is equal to, let's start by this one. This is basically X bar Y plus the A here is. So when we write this, just to consider it for a moment as 1, for a moment. So just imagine this A is 1. So if this A is just 1, so this group will be XY bar. Then multiply by the A. Okay? We multiply by the, then plus again for the B, this group here, which has B. Okay? Just imagine for a moment it's 1. So if it's 1, this group will be XY. Then multiply by B. Okay? And let's now check if we are correct or wrong. Okay? Let's put F equal to 0, 0. If, I'm sorry, XY is equal to 0, 0. If we put XY is equal to 0, 0, this will be 0. This will be 0. This will be 0. So F will be 0. That's good. Let's put F equal to 0, 1. I'm sorry, XY is equal to 0, 1. So Y is 1, X is 0, but X bar will be 1. So this will be 1. Don't continue, because 1 or whatever will give you 1. That's correct. Now the third case. X is 1, Y is 0. When Y is 0, this will be 0. Here X is 1. Good. Y 0, but Y bar will be 1. So this will be give you A. Then here in that term, the third term, Y is 0, so this will give you 0. So this will be basically 0 plus A plus A plus 0. This will give you A. Exactly what we want, like the truth table. Finally, 1, 1. So this will give you 0 because X bar will be 0 plus again 0 because Y bar will give you 0. Then 1, 1, B, which is basically B. B 0 plus B is just B, which what we have here. Okay, that's very nice. Okay, this is the first observation, how to deal with a truth table that has not only zeros and ones, that also have some variables. Okay, and we know the physical meaning of these variables. It's just inputs to the circuit. Okay, good. This is the first observation that I want to take into account. Second observation is we didn't see before, the simplest Karnaugh map that we discussed is this one here, which is a Karnaugh map in two variables. But if we have a function in one variable, like this, for example, x and f, so this is basically a very simple circuit, one input and one output, 0, 1. So when x is 0, for example, f is 1. When x is 1, f, which is basically inverter. We know that f is equal to x bar. But let's prove this. How we can apply Karnaugh map to do that? Basically, the simpler Karnaugh map now is the one that has for one variable, which is 2 squares. Look, here we have 4 squares because we have 2 variables, so 4 combinations. Here we have one variable, 2 combinations, so we have only 2 squares. So this is x, of course, the second order x bar, just that's it. So when x is 0, which is basically x bar, f is 1. When x is 1, which is basically x, f is 0. So we have here 1, 1. So just one group. So this group is f equal to x bar. And we know that this is really x bar because when x is 0, the output is 1, it's the opposite. When x is 1, the input, the output is 0, is the opposite again. Okay, that's basically, and we can take another example, x and f, 0, 0, 1, 1. So in that case, let's draw the Karnaugh map for one variable, x bar. X is 0, x bar means 0, so this will be 0. X is 1, so f is 1. Again, one group. This group f equal to just x. Okay. That's basically how to deal with a truth table with variables in it and a Karnaugh map for just one variable. So let's apply such concepts to that truth table here and try to get benefit out of it. So let's copy it and paste it, in the bottom of the page and try to deal with it. Okay. Now, so let's now go back to the circuit and see what we want to do. We want to get functions for x, and x here is a binary variable, okay, that has 4 bits, just like a and b, and y and c. So these are, we can consider them, we can consider the outputs, but don't confuse them with the output of the circuit, which is the sum and the carry, please. Okay, this is just internal problem that has inputs and outputs as well. Okay, don't confuse x and y, because I will call them outputs with the output of the circuit. Okay, it is just a sub problem. Okay, that's good. So these are our outputs, and again, don't confuse them with the sum and the carry. And here is our input. I'm sorry, this is our input, M. Okay? This is just to choose the operations, not part of the truth table, just to choose the operations. That's it. So basically, you have one input here and 3 outputs. Okay? And the truth table here has zeros and ones and also variables. Okay, let's do it. So let's start by xi. So we have a Karnaugh map M and M bar. Okay. When M is 0, which is M bar, X is AI. When M is 1, which is M, we have AI as well. Okay. That's very nice. Now we have a group here, and this group is basically this one. Okay. And this group is AI. So F equal to AI. And just, I know that you are confused. So let's prove it, okay? You can have two groups. Let's assume you have two groups. Let's do this with another color. So this is a group, and this is another group. This group will give you M, AI. Just, review what we have did here, okay? And this group is M bar AI. So F is equal to M AI plus M bar AI. Now you can take AI as a common factor. This will be if M plus M bar. This is basically 1. So this is AI, right? That's basically what we did, okay? And just to compare it to this situation, if you have, a function like this, M bar, although it's not and 1 on 1. So we have here all that. So F will be equal to 1. But we said that whatever you do, whatever you get, just imagine for a moment it's 1, then multiply by A. So we're going to multiply by A. So F is equal to A. Okay? That's basically what we did in our review here. Good. So basically, we drive it now that F here is basically Xi. So just write it as X, not to confuse anyone here. So we just drive it here that Xi equal to AI. Let's do the same for Yi. Again, M bar. When M is 0, which is M bar basically, Yi is Bi. When M is 1, which is M, Bi bar. Okay? Bi bar. And these are not similar. You cannot combine them. You can combine anything similar, but this is B and B bar, like 0 and 1. You cannot combine them. So we have two groups here. This is a group, and this is another group. So Yi is equal to. So let's start with the Bi group. Imagine for a moment it's 1. If it's 1, this will give you M bar. Then multiply by Bi. Then plus. Let's go to the second group, which is Bi bar. Imagine for a moment it's 1. So this will give you M. Then multiply by what's inside the cell, which is Bi bar. What is this? It's like X, Y bar plus Y bar X. This is basically the XOR. So this is basically M XOR Bi. Finally, let's do the C. That's, very simple. M bar. When M is 0, which is M bar, C is 0. When M is 1, which is M, this will give us 1. So this is one group. So CO or C0 equal to basically M. So let's now compare. X is equal to AI. Yes, X is equal to AI. Xi is equal to AI. Yi is M XOR Bi. Exactly. C is equal to M. C naught is equal to M. C naught is equal to M. So that's, the way how to do it. You can just, because it's simple, very simple table here, you can just deduce functions by yourself. You don't need any formal proof. But if you want a formal proof, here is the formal proof. Okay? And I like that, by the way. Okay, guys, thank you very much for watching this video, and see you in the next video. Bye-bye.